All right, welcome back to our fifth and final part on correlations. So this fifth part, like the fourth, is going to involve some more math. Thankfully, the math is fairly straightforward. So one thing you might want to do after you've calculated a correlation when you report it is report the confidence interval, typically a 95% confidence interval. So up on the screen here on that first line, we see our typical formulas for calculating confidence intervals. So the first with a z-value if you have greater than 30 participants, and then if you have less than 30 participants, you would do so with a t-value. We can't use those straight away with correlation coefficients because correlation coefficients are not normally distributed. So they're violating one of the assumptions of our typical parametric tests and formulas like calculating confidence interval. The good news is that we can transform them so that they are normally distributed, the correlation coefficients. And that would give us an updated confidence interval formula that looks like the following. So instead of putting in a mean here, we're going to put in a correlation coefficient value, but this is a transformed value denoted by the z value here. So this is r sub z, and we'll talk about how to calculate that. To get the standard error, we can't calculate that, but we can estimate that. There's a simple formula for estimating our standard error. And these formulas are the same. The only difference is, are we using a z value or a t value? So how do we transform r to r sub z? Now this is known as Fisher's transformation, and this is the formula for it. So it looks a little complicated at first. We have a logarithm, and that log is to the base e. Now e is a mathematical constant, and this doesn't have to be too scary. So pi is another mathematical constant of 3.14. Now e happens to be Euler's number, and the value is 2.71818, I think. And log to the base e is also known as the natural log. So we're using the natural log here, and within that we put in our r value, our correlation coefficient. We divide these, take the natural log of that, multiply 1/2, and we get our transformed r value, our r sub z value. The standard error, its formula is quite simple. We take 1 and we divide it by the square root of the number of participants minus 3. So the standard error is completely dependent upon the number of participants or data points. So what does that transformation look like from r to r sub z? Let's just take a look at it here. I'm trying to move this out of the way a little more, if it will let me. There we go. Okay, so the red line, those are possible correlation coefficients, and recall that they range between -1 and 1. And then after they're transformed with that formula we just saw, what happens is values around 0 are basically identical between r and r sub z, very little change. And even between -0.5 and 0.5, yeah, around here there's a visible difference, but pretty tiny changes. The big changes are occurring for large correlation coefficients. So when they're larger than 0.5, that r value is going to get much larger when it's an r sub z value. If you happen to have a perfect correlation of 1, its transformation actually is infinity. If it's anything less, like even say 0.999, you're going to have a value that's a bit lower, or around 3. So that transformation makes our correlation coefficient normally distributed, and then we can use that updated formula to calculate our confidence interval. So let's look at an example of that, and for this we're going to use the simple data that we just looked at, where there was only 5 participants. So the correlation coefficient here was 0.871. The first thing we'll do, the easier step of the two, is to calculate or estimate our standard error. So we are going to put our numbers into the formula here. All we need to put in is that 5 for the number of data points, or participants in this case. So our standard error, our estimate for it, is 0.7071. Easy enough. Now we need to transform a correlation coefficient from R to R sub z. So we're going to use this formula, and we're going to put in our correlation coefficient, 0.871. We'll do a little bit of math here. We can use a calculator or Google to calculate the natural log, and we're going to get an R sub z value of 1.3372. And it makes sense here. So our R value is about 0.7, and what we would expect, because it's larger than 0.5, remember that green line was getting bigger, so the R sub z value should be a bit bigger than 0.7, and it is. It's about 1.3. So we've got everything now to calculate our confidence interval. Because we only had 5 participants, we're going to use a t-value. So we plug in our R sub z value and our estimate of the standard error, which is also being transformed into into a z value or the z domain. Now for the t value, we would look this up. So the degrees of freedom here for t value, for correlation, it's n minus 2. So we've got 3 degrees of freedom, and we want to look up a two-tailed t value. We actually did this a little earlier, and let's see, I forget it off the top of my head. There we go. It's 3.182. If you go to I think it was in part 4, I showed you looking up the t-table and the column and the row and where they intersected. That was the value we wanted. So we multiply this out, and we're going to see that our confidence interval ranges from negative 0.9 to about 3.6. Now this isn't the confidence interval we would want to report because it is in z values, which although are what we need to use for the formula, it doesn't really make sense to report because we're used to seeing correlation coefficients as R and not R sub z. So we need to back transform this now into R values. So Fisher's transformation, there is a transformation from R to R sub z, likewise from R sub z to R. And we saw the kind of the complex formula for R to R sub z before. And if you've done some math before, you may be thinking, hey, I recognize that formula. And yes, this formula is, let's see if I get this right, the inverse hyperbolic tangent function, or tan h minus 1, noting inverse. And if you're doing this in MATLAB or programming language, probably even Excel, the formula is typically a tan h, a denoting inverse. And we can convert R sub z to R with this, somewhat complicated formula that doesn't have a logarithm but still has Euler's number of or constant e. But instead, it's probably just easier to use the trigonometric function here of this formula, which is the hyperbolic tangent function. So not the inverse, just the hyperbolic tangent function. And these two functions, of course, are the opposites of each other. So we want to do this for our confidence interval. So we already know that 1.3372, we already know that correlation coefficient. I think it was 0.871 off the top of my head. But we need to look up the lower part of the tail, or transform the lower part of the tail and the upper part of the tail from R sub z to R. So for the lower part of the tail, we're gonna plug it into this hyperbolic tangent function, and of course, you can look this up on Google or use MATLAB or Excel, and we get an R value, which we're used to looking at R values, is negative 0.7. And at the other side, this is a fairly large value. Remember I said if it's very close to 1, it's going to be around 3. So this is slightly above 3, so it's going to be very, very close to 1. And sure enough, it is. It's 0.9985. So up top here, we would not report the confidence interval in R sub z values because that's strange. We want to back transform to R values, and we would report the confidence interval as such. So the correlation coefficient is 0.871, and in this case we calculated a 95% confidence interval, which is the typical interval that's used, is from negative 0.7 all the way up to 0.1. So that's a pretty wide range. We're saying that correlation, if we did this experiment again, the actual population value could be anywhere in there, and that's because in this example, we had 5 participants. It's a tiny data set. So that math we just looked at will allow you, with kind of similar rationale, to do a few other calculations. First up, you can compare a correlation to any value. So in SPSS, when you run a correlation, it compares to see is it significantly different from 0, from no correlation. But you might instead want to see is it significantly different from, say, 0.5. So to do that, so 0.5 would be your estimate at a correlation value in the population. So it's not just in a sample, but that's your estimate of the population correlation coefficient. And the way that is denoted is here with the lowercase p, or rho. And again, because they're not normally distributed, we need to convert that into a z value. So here we're denoting that as rho sub z. So you take the correlation that you found, convert it to r sub z, subtract your transformed population correlation coefficient, and then divide by this term, and that will give you a z value, which you can then compare to a critical value. Instead, we're going to do the second example. So this is comparing two independent correlations. So let's say you've done two studies. In the first, you have one correlation value. In the second, you get another. And you want to know whether they're significantly different from each other. Because it's likely they'll both be significantly different from 0. That's not often that interesting, but are they different from each other? And that can be done with this calculation here. A quick note on why I say why these are independent correlations. So this doesn't have to do with within or between designs. It means that the same data was not used twice, which is kind of a similar concept. So for example, if you had three variables, A, B, and C, and you correlated A and B, and then you correlated A and C, so you've used two of those variables twice, those are not independent correlations because both of them share half of the same data. So this would be when the correlations are different data sets. So it could be A and B correlated in experiment 1, A and B correlated from a separate data set in experiment 2, or it could be in one experiment you're looking at the correlation between A and B and then C and D. So non-overlapping data is when you can use this formula. And the logic to it is basically we're going to calculate a z-value, and we're going to compare that to a critical z-value of 1.96 to see whether there's a significant difference. So here's an example of that. So the first part of the data is the data we actually, which I got from my class. So 82 students, the correlation between attendance and grade was negative 0.601. That's the value after we removed outliers, which would be the best data to look at. And then the second part I've made up, I haven't actually done this twice yet, but let's just pretend that in the next semester, 85 students now had a correlation of negative 0.501. So if you run this experiment twice, different participants, there's factors that change. You don't expect exactly the same value, but are they comparable or are they significantly different? So these are the four different data points that we're going to need pulled out of the text there. And the first thing we're going to have to do is transform our correlation coefficients, our R values, to R sub Z values. So a little quick math here, and the first one is going to be negative 0.6947, the second one is negative 0.5506. You can see that there is very little change in these values, and that's because if you remember the red line and the green line, they're pretty much overlapping between 0.5 and negative 0.5. So very little change with the transformation from R to R sub Z. Okay, so we now have everything we need. We can plug that into the formula and crunch these numbers, and we're going to get a Z value of negative 0.9143. Now this is a Z value, so we can compare this to our typical 95% Z value of 1.96. So if our Z value, the absolute value of it, is significantly, if it's greater than 1.96, then we have a significant difference. And if it is less than that, then we don't have a significant difference at a p-value of 0.05. So our z-value is 0.9143, so we don't need to worry about the sign. Just think of the absolute value is less than 1.96, So our two correlations are not significantly different. So the p-value is going to be greater than 0.05. Our very last thing I want to mention, in these cases we've talked about when you get a whole bunch of data, say in the classroom example, so everyone has a grade, everyone has a number of absences, and then you correlate them for a single correlation. So we've talked about, okay, well, let's make a confidence interval for that, let's compare it to 0, and so on and so forth. It's possible, though, that in your experiment, you might have a single correlation for every participant. So think of an example when that might happen. Let's say you have a participant doing a reaction time experiment, and they get a reaction time and a movement time for each trial. And let's say they do 100 trials. Well, what you could do for each participant is look at their 100 reaction times, look at their 100 movement times, put them onto a scatter plot. You're going to have 100 little dots, and then you could calculate the correlation. And if we look at the table over here, let's say we've done that, and I think there's 36 participants in this data set. So the first one, they happen to have a negative correlation between reaction time and movement time. These numbers are just made up, but trying to give you some context. And then let's say you tested that participant not just in one movement condition, but 3 different movement conditions. Maybe an easy condition, a medium condition, and a hard condition. So for each one of those, you could calculate a correlation. So it's not that all of our data results in a single correlation, but we actually have a correlation, an R value, for each participant, and maybe even in multiple conditions. So you might be wondering, when you have data like these, can you run normal stats on them? So could I do a one-way ANOVA with 3 levels? The answer is yes, you can. But we do still need to correct these data because correlations are not normally distributed. So we're going to take our correlations, our R values here, and we're going to use the inverse hyperbolic tangent function, and we're going to calculate the R sub z values, which are shown here. Once they've been transformed, they're now should be normally or more normally distributed, and you can now run a one-way ANOVA, you can run a t-test, you can do your typical parametric procedures. You could even calculate confidence intervals in a normal way here. You don't have to use the formula we just looked at. So I won't test you on this on the assignment. I just wanted to mention it in case in your research you're not just generating one correlation, but you have a correlation for every participant and maybe even in multiple conditions. You can use those like normal data once they've been transformed. To wrap up here, next Wednesday we'll have our tutorial on Zoom. I'll send out an invitation for that. The following Tuesday, the correlation assignment will be due. The day after that, we'll have our last class, which I think will be on YouTube again, unless this goes poorly and I find this delivery method doesn't work for a lot of people. Then maybe we'll try to do the class, our last class, on Zoom. But thank you all, and let me know if you have any questions even before the tutorial, after the tutorial. You can email me. We can set up a Zoom. I've done that with several of you already. It's really handy. We can share screens, work on numbers. So let me know what questions you have, and I look forward to seeing you in digital person on Zoom next week.